The most commonly repeated definition of Euler's number is that its natural exponential function, e to the power of x, is its own derivative. Through that simple property, e is in every corner of math and science. From half-lives to charging to heat transfer. E's connection to geometry is less clear. Not that surprising when you consider that E is defined by its relationship to calculus and not geometry like pi. By randomly generating points in a square with an inscribed circle and noting the ratio of points inside the circle relative to the total, we can estimate pi to reasonable accuracy, a process known as Monte Carlo simulation. Surprisingly, there exists a similar model for estimating E. In order to understand how that works, let's explore the many definitions and instances of E. One last note before we begin. This exploration requires a bit of calculus to connect some of the definitions together. Further reading and videos on each of the calculus subjects touched upon in this video can be found in the description. In order to begin our exploration of E, let us use the Taylor series of e to the x to determine a series equal to E. For our purposes, a Taylor series is a series of polynomials used to estimate a non-polynomial function, such as e to the x or sine of x. For example, the Taylor series for sine of x is x minus x to the power of 3 over 3 factorial plus x to the 5 over 5 factorial and so on. As you can see from the graph, as each term of the series is added, the Taylor series becomes a better and better approximation for sine of x. Thus, at infinite terms, the series is the same as sine of x. The simplified steps for finding a Taylor series are as follows. If we want our series to represent the original function as best as possible, we need them to share as many attributes as possible. For a line, we would want them to share common slopes and intercepts. However, more complicated functions do not always have constant slopes. Thus, we should match their derivatives, measures of how the functions change over small intervals, in order to ensure that the functions are as similar as possible. First, let us ensure that our series and the original function share the same y-intercept. As long as the only constant term in the series is the intercept, the value of the function at x equals 0 will be the same as the constant. Thus, since e to the x at x equals 0 is 1, and the first term of our series is 1. Before we continue to the next term, let us define a couple derivative rules. The derivative of a constant or constant function is 0. The derivative of any polynomial term, x to the power of n, is n times x to the power of n minus 1. For example, the derivative of x squared is 2x, and the derivative of x to the power of 3 is 3x squared. For our next term, we want the derivatives of the series and the function to be the same, so that their values increase at similar rates. Since the derivative of the constant term is 0, the only term that contributes to the first derivative of our series is the term with a degree of 1, the term in the form cx. Since the original definition of E is that E's natural exponential function, e to the power of x, is its own derivative, the derivative of e to the x is simply e to the x, or 1 at x equals 0. Thus, our second term is 1x. Note that if we were to take the derivative of our series so far at x equals 0, it would simply be 1 from the term we just added. We also want to match the second derivatives of the function so that our series closely hugs the function even as the first derivative changes. Since the derivative of e to the x is also e to the x, the second derivative of e to the x is also e to the x, or 1 at x equals 0, which would make the next term seem like 1 times x squared. But remember that when we take the derivative of this term, x squared becomes 2x, and the second derivative becomes 2 times 1, or 2. Thus, in order to make sure that the second derivatives of our series and the function match, we divide the term by 2 times 1, or 2 factorial. Repeating this process for the third and fourth derivatives, we find the next two terms of the series to be x to the power of 3 over 3 factorial and x to the power of 4 divided by 4 factorial. As each term is added, our function begins to match e to the x closer and closer. It is also interesting to note that the terms in the series for e to the x follow a pattern. The nth term of the series is x to the power of n over n factorial. At infinite terms, our series and e to the x would be equal. So e to the 1 equals the series at x equals 1, or 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, and so on. Even a sequence of just the first 4 terms is already about equal to e. This result is actually incredibly interesting in its own right, and actually has plenty of applications which are beyond the scope of this video. But for our purposes, it is most important for validating the limit definition of e. The limit definition of a derivative is limit as h approaches 0 f of x plus h minus f of x over h. Since we're working with the derivatives of e to the x, it would be nice to have some sort of limit definition of e to the x. Turns out there are two identical limit definitions of e. Limit as n approaches infinity of 1 plus 1 over n raised to the nth power, or limit as n approaches 0 of 1 plus n raised to the 1 over nth power. First off, let's confirm numerically that these limits are equal to e. From the table below, it is clear that as n approaches infinity, the limit approaches e. Now, let's see how this connects to the factorial definition we derived earlier. When expanding a binomial, such as the inside of the previous limits raised to a power, instead of manually distributing and combining like terms, we can use Pascal's triangle to find the coefficients of each term. Let's take the expression x plus y to the power of 2, which is equal to x squared plus 2xy plus y squared. If we were to look at the coefficients of each of the terms, we would find that they are equal to the numbers in the second row of Pascal's triangle. Remember that the top row of Pascal's triangle is indexed as the 0th row. For x to the power of 3, the expression is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed, the coefficients matching the third row of Pascal's triangle, as does the expansion of x plus y to the power of 4. Notably, we can find the kth index of the nth row using the formula n choose k. For example, 3 choose 1 is equal to the first index of the third row of Pascal's triangle. Remember that the leftmost number in a row is indexed as the 0th number in the row. Thus, the general form for the expansion of a binomial raised to a power is n choose 0, x to the power of n, y to the power of 0, plus n choose 1, x to the power of n minus 1, y to the power of 1, plus n choose 2, x to the power of n minus 2, y to the power of 2, all the way to n choose n, x to the power of n minus n, y to the power of n. Take a second to ensure that this result makes sense. For our purposes, we want to expand the inside of the limit 1 plus 1 over n raised to the nth using the binomial theorem. For now, let's just blindly plug this into our equation. When we do, we get the equation shown. Note that all of the 1 to the n terms simply are equal to 1 and can be ignored from the products they're a part of. Then the equation simplifies down and becomes the equation shown. Also note that we can expand the combinations in the form of n choose k with the equation we used earlier, n factorial over n minus k factorial, k factorial. That results in the equation you see. As the numerators and denominators of each term largely cancel, we're left with terms of equal power on the top and the bottom, and an additional numerical factorial on the bottom. For example, the yellow text shows how n times n minus 1 over n squared is equal to 1 as n approaches infinity, a process which repeats for each term in the expression and results in only the numerical factorials being left over. Thus, we can be certain that this limit is truly equal to e because the factorial definition for e matches what we have left from this equation, and we can derive a bunch of very useful e-related derivatives and integrals. First off, we can verify that e to the x truly is the function whose derivative is itself. Using the definition of derivatives shown earlier, the derivative of some exponential function a to the x is the limit as h approaches 0 of a to the x plus h minus a to the x over h. A to the x plus h can be simplified into a to the x times a to the h using an exponential property. Then we can pull out a to the x from the numerator and the limit in general because it's not dependent on h, resulting in the equation shown below. Then we can substitute b equals a to the h minus 1, which means h equals log base a b plus 1, and b approaches 0 as h approaches 0, resulting in what you see here. Then we can change the numerator into 1 over b, which allows us to move 1 over b into the denominator. Using the log property shown, we can move the 1 over b into the power of b plus 1. And then, swapping the limits and the logs, we can note that the limit shown, limit b approaches 0 as b plus 1 raised to the 1 over b power, is equal to e, resulting in the fraction equaling 1 over log base a of e. Then, since log base a of a equals 1, we can substitute the numerator with log base a of a. Then, using the base change property of logs, the fraction simplifies into natural log of a. This tells us that if and only if a equals e, the derivative equals a of x, and a of x is a function whose derivative is itself. For reasons that will become clear shortly, we also need to prove the derivative of natural log of x. Starting with the definition of derivatives, we can see that we can combine the natural logs using the properties shown, resulting in natural log of x plus h over x over h. Then we can pull the denominator out of the natural log, resulting in the equation you see. Then, using the property shown, we can move the 1 over h to the power of 1 plus h over x. Then, we can substitute c equals h over x, which means 1 over h is 1 over cx, and c approaches 0 as h approaches 0 to get the equation you see. We can separate the 1 over cx using the exponential properties shown, resulting in having a 1 over x, which we can pull out using the log property shown. We can pull this out of the natural log and the limit because it's not dependent on c. Then we can swap the limit and the log, resulting in the equation shown. Then we note that the limit as c approaches 0 of 1 plus c raised to the 1 over c power is equal to e. And since the natural log of e is 1, we note that the derivative of natural log is 1 over x. One last property. When finding the definition of a definite integral, we use the antiderivative of the function inside the integral. An antiderivative is a function that, when you take the derivative of it, returns the original function. For example, the antiderivative of x is 1/2 x squared, because the derivative of 1/2 x squared is x. Similarly, the antiderivative of 1 over x is ln x. Now, after all of that, we can finally reach the really cool demonstration of E promised at the beginning of the video. Our goal is to create some geometric area so that when we place random dots in some region on this board, the ratio of the number of dots in one part of the area to the total number of dots is connected to E. Remember that just now we discovered that the antiderivative of 1 over x is ln x. Well then, the definite integral from 1 to e of 1 over x dx is equal to the natural log of e minus the natural log of 1, or 1 minus 0, or 1. The physical meaning of an integral, though, is the area under the curve between the bounds is equal to the value of the definite integral. In this case, that means that the area under the curve 1 over x between 1 and e is 1. Thus, if we draw a rectangular region of base e minus 1 and height h at this point on the x-axis as our total region, the ratio of dots under the curve, the red area, to the total number, the red plus the purple area, is equal to 1 over e minus 1 times h. Rearranging, we find that e equals 1 plus the total number of dots divided by the number of dots inside the red area times 1 over h. One last wrinkle before we can declare this model complete and finally estimate e with it. What do we set e as before the program starts? Because our definition for e contains an integral with e as a bound, our model for e requires e as a starting parameter. Luckily for us, this model converges to a value close to e for any starting value of e, given enough iterations. As such, we will start e as some guess for e, and then have the program use a new value of e for the next iteration of the model. So, even if we started the model with a guess of e equal to 10, the model would eventually converge to e. This model starts with e equal to 4 and slowly refines its guess towards the actual value of e. And now, finally, we can run the program and see that out comes e, hiding in the area under the simplest rational function and some clever bounds. And hopefully, after this exploration, you can see e there too. Thanks for watching. This is a submission for 3 Blue 1 Brown's Summer of Math Exposition 2, and uses the Manim engine for many of its visuals. Thanks goes out to the creator of 3 Blue 1 Brown and the community developers of Manim. Hope you all have a great day.